Hello, hello, hello. This is Nicholas, and I had the fun video I wanted to do. It was about matrices and determinants. So a lot of people, when they first kind of talk about matrices, they're usually shown like a 2x2 matrix. Say in general, it would be like A, B, C, D. And then they're shown about this thing called a determinant, right? A determinant of a square matrix, meaning that the number of rows and the number of columns are equal. And they're just kind of taught magically that this formula is AD minus BC. And they kind of go through a bunch of examples computing this, and that's really about it. That's where it, or they'll go to the 3x3 determinant, right? Like A, B, C, D, E, F, G, H, I. And then they'll learn I guess kind of the formula for, in general, how to compute a determinant of a square matrix by expanding by minors, right? So you could go along this row and that column, and you'd have A times the determinant of that matrix, and so on. The purpose of this video is not to define those formulas, because technically you can't prove them. They are by definition. But the purpose of this video is to kind of motivate why that would be a good definition, and to show some properties that the determinant has. Namely, the one most interesting property, then that's what I'm going to prove in this video, is about the relation between determinants and volumes of solids, or areas of like parallelograms, 2D figures. So to start off with, let's consider the xy plane. So we're in 2 dimensions right now, and let's consider a vector, two position vectors. So with tail at the origin, say vector A and vector B, and I'm gonna well, first of all, let me say I'm gonna point out that these two vectors can uniquely define a parallelogram. We say that they define a parallelogram spanned by vectors A and B. And so what that means basically is, so you'd copy vector A along here so that its tail is at the head of B, and then you'd copy vector B so that its tail is at the head of A, and you have now this parallelogram right here. And I've done a video with the cross product and explaining what that is, how to compute it, why it's useful, all those things. And so from there, I know that the area of this parallelogram is the magnitude of the cross product between those two vectors. Now, the other thing I want to point out is that if we treat these vectors, say, let's call them a sub 1 comma a sub 2, so like the scalar components of them, basically, is what I'm writing. So if we have the matrix then composed of those two vectors, and we like have these row vectors basically. So we have the matrix A, vector B, and so you can't technically write a matrix with vector entries, because the matrix is defined with scalar entries, so we'd replace that with a sub 1, a sub 2, b sub 1, b sub 2. That's why I wrote out these scalar components here. Then it turns out also that the area of this parallelogram spanned by these two vectors, which for the rest of this video I'm going to denote as the parallelogram spanned by vectors A and B. Right, because those are parallel lines. That's kind of where the notation comes from. I don't know. This isn't just me, but it's probably, there's not really a specific way to denote it. So I just kind of come up with my notation, but it is used before. It's not just me making this up. It's used in like certain multivariable calculus books. But anyway, yeah, this determinant, the magnitude of it, because right, we can't have a negative area, turns out to be the volume of this, or I'm sorry, the area of this parallelogram. And it's very straightforward to prove this fact, and especially in 2D. I'll kind of set you up for the proof, and then I'm going to kind of leave it to you to actually prove it. But the idea itself is very simple in 2D. Basically, you can just consider the rectangle that I just drew in, that red rectangle, and you can do rectangle minus kind of extra stuff, basically. So you can also divide this here, so that now you get a triangle. Oops, I still have the straight line tool. A triangle, right? You're going to get another triangle. That's the same triangle as the other one I just squiggled in. And then you're going to get this triangle and then this triangle, which are going to be the same. And if you just subtract the area of the rectangle from the area of the blue and red triangles, you're going to get, well, in this case, you'd get a sub 1, b sub 2, minus b sub 1, a sub 2, right? That's the determinant of that 2 by 2 matrix. And if, you just find the area of the rectangle, find the area of those triangles, subtract them, you're going to get this. Or you might get the negative of it. And that just depends on kind of how you do the subtraction and the labeling and everything. But that's perfectly fine because we're talking about the magnitude of the determinant. And so the magnitude of negative of all of this just gets rid of the negative sign. So either way, if you get this or the negative of it, you're fine. You proved it. So now, this type of proof is really only, you can use it in 3D as well, although that would get a little harder because it would require more visualizations, more triangles, more volumes to compute, things like that. So it would get a little messy. But it turns out that in general, and this is what I'm going to spend the bulk of the video proving, is that, and I kind of want to write it out because it's really powerful. It's one of the main uses of a determinant, right? Maybe not main, but it's a very powerful fact that kind of gives motivation to the definition. No, I don't want to stop recording. So the theorem is that the absolute value, which I'll just write as abs, of an n by n square matrix is equal to the, you could call it hypervolume, right? Volume in n space of the hyperparallelepiped spanned by your n vectors. So spanned by, say, vector x sub 1 up to vector x sub n. So kind of breaking this down some, if we were to imagine in 3D spanning a parallelepiped, that's what parallelepiped is. It's like basically a 3D parallelogram. Every side of a parallelepiped is a parallelogram. So in 3 space or in R3, however you want to denote it, that was kind of a bad R. Let me see how it's, that's how it's drawn, R3, that's 3 space. The reason why is because it's R cross R cross R. 3 real number lines. That's where the motivation for that notation comes from. So in R3, to just give you an idea of what the parallelepiped spanned by 3 vectors would look like, I'm going to do my best to draw here. 3D drawing is not my strong suit, but I'll try. So, and that axis is, I gotta be, the axes, if you don't get the axes right, it's just all gonna fall apart from there. So I gotta make sure I get these really good. Okay, call this X, Y, and Z. So they're all mutually perpendicular axes. And so let's say we have a vector A, a vector B, and a vector C kind of coming out at you. So you could kind of imagine a parallelepiped spanned by those 3 vectors. And so you could basically consider how a parallelepiped might be spanned by, say, those 2 vectors and those 2 vectors. Or I'm sorry, how a parallelogram might be spanned by those 2 vectors. And then you could do by those 2 vectors. And then you could do by these 2 vectors. And when you kind of take the union of all those parallelograms, you're going to get a parallelepiped. And you can Google what a parallel pipehead would look for yourself, but honestly, if I try to draw it, it's going to look worse. But realize, though, that it's just a natural extension of how we did it right here in 2 dimensions. It's just hard to draw for me. Okay. And so, in general, it takes n vectors to span a n-dimensional parallelepiped in n space. So, in other words, if we have the determinant of the matrix made up of the row vectors, say, x sub 1 down to x sub n, right? So that's just a compact way of writing it, because I don't want to write all the n scalar entries for all of the n vectors, right? That would take a while. So the determinant, though, of that matrix, the absolute value of it, is equal to the hypervolume or volume in n space of the, say, hyperparallelepiped in n space spanned by the vectors x sub 1 to x sub n. And so this is what I'm going to prove. It's a very powerful tool. So that's why, for example, in the case of 3 dimensions, that's why the cross product is defined through a determinant, because the magnitude of the cross product, which is the magnitude of the determinant of a matrix, gives you the volume of a parallelogram. And it's a parallelogram in that case because cross product is only between 2 vectors, not 3. Of course, if you have vector A dotted with B cross C, then you would get the parallelepiped spanned by A, B, and C, that volume. That was in a previous video, though I don't want to spend my time on that. So, how can we prove this? Well, the first thing that I want to notice is that in this n by n matrix with all of those row vectors, notice that all the vectors, I'll write it out because I think it's important. All the vectors from x sub 1 to x sub n, they all need to be, they need linear independence, basically. So linear independence, what does that mean? It means that you could not write, say you were to pick any random vector, say you were to pick x sub 7, right? That vector x sub 7, whatever it is. What it would mean for x sub 7 to be linearly independent of all of the other n minus 1 vectors is that you couldn't write x sub 7 as a linear combination of any of the other vectors. So if you don't know what a linear combination is, this is kind of getting into linear algebra now. A linear combination of these n vectors would be of the form some constant c sub 1 times the vector x sub 1 plus another constant c sub 2 times the vector x sub 2 plus yada yada plus another constant times the nth vector, where at least one of those constants is non-zero. And so that's a linear combination, and hopefully you see why we call it that, because it's just in the form of a linear equation of n variables. There's no wacky exponent here like a 2, it's just constants times a variable, right? And so that's why we call it a linear combination. So all of these n vectors need to be linearly independent. And so if they're linearly independent, what that means is that one could not be, say, a scalar multiple of another vector, right? So for example, x sub 1 could not be equal to some constant times x sub 2. Oops, I wrote the times x sub 2, right? Because if x sub 1 were a scalar multiple of x sub 2, imagine this in 2 dimensions, for example. Let's call this x sub 1. Oh, let's call this x sub 1, the vector x sub 1. Now, if if these two are scalar multiples of one another, then what that means is that they're parallel, because you still are going in the same direction. It's just a different magnitude, right? Same direction, but different magnitude. So if these are parallel, then say maybe x sub 2 is like a longer vector, right? Just a different magnitude, but in the same direction. And if you were to determine, since we're in 2 dimensions, if you were to try to determine the area of this parallelogram spanned by these 2 vectors, well, it's 0, right? These 2 vectors coincide with one another. They just form a line. And so basically, you lose a dimension in your calculation, right? So if you have one vector that's a scalar multiple of another, meaning they are linearly dependent, then you lose a dimension in your calculation. So what that would mean in n space is if you've got n vectors, but if any one of them, even just one, is linearly dependent, then that means that your parallelepiped in n space would not actually be living in n space. It would be living in like n-1 space or n-2 space, because it might lose a dimension if you have the vectors overlapping, if they're scalar multiples like this. And so then the volume in that n space would always be 0, and we don't want it to be 0, so we need the condition of linear independence. Now, the bulk of this, so the hardest part of proving this theorem, is that linear independence implies independence. Did I spell independence? Yeah, no, I didn't spell that wrong. Implies diagonal, this is kind of a long word, diagonalizability. And so what does it mean for a matrix to be diagonalized? It means you turn, for example, a 3x3 matrix. If you turn a matrix, say A sub 1, A sub 2, A sub 3, B sub 1, B sub 2, B sub 3, C sub 1, C sub 2, C sub 3, into a matrix with different constants, say R sub 1, R sub 2, R sub 3, and then with zeros everywhere else, so non-zero entries only along the main diagonal, then we would say that this matrix right here is diagonalized because it only has scalar entries along that main diagonal. This main diagonal, to be specific, not that main diagonal. Okay, so why is a diagonalized matrix useful? I mean, what's the point of considering a diagonalized matrix? Well, the point is that then the determinant of this matrix, let's say we call this matrix A, the determinant of A is just R sub 1 times R sub 2 times R sub 3. Why? Hopefully you can see it pretty obviously. If we were to expand by minors, we would get R sub 1 times the determinant of the matrix R sub 2, 0, R sub 3, 0, R sub 3, plus 0 times this matrix, which is 0, plus 0 times this matrix, which is also 0. So we just have this part right here. And then if we were to take the determinant of the matrix itself, we get R sub 2 times R sub 3 minus 0. So we just get R sub 1, R sub 2, R sub 3. And hopefully you could see it's the exact same reasoning if you've got an n-dimensional matrix. You just multiply across by the n entries along that main diagonal starting from the top left corner. And so that's why a diagonalized matrix would be useful. Now basically we need to be able to go from a linearly independent matrix made up of a vector rows, where each row is a vector that spans the parallelepiped, and using only what's called Gaussian row operations, we need to go from the original matrix to the diagonalized matrix. I'm kind of assuming that you've seen Gaussian row operations before. Basically, that's saying that if you, for the purposes of this video, the main Gaussian row operation that you need to know is that if you add any linear combination of any row of the matrix to any other row, it won't change the final determinant. So for example, 1, 2, 3, if we have this matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's say I were to add, I don't know, let's do 2 times row 2 plus 3 times row 3. And then I were to add that to row 1. So row 1 is going to go to 2 times row 2 plus 3 times row 3 plus row 1 itself. So row 1 would become, we would have, say we have 1, 2, 3. You normally don't write it like that. You normally write, we'd have 1, 2, 3 plus 2 times row 2, so 2 times 4, 5, 6 plus 3 times 7, 8, 9, which would be 1, 2, 3 plus 8, 10, 12 plus 21, 24, 27. And then you would add up the corresponding numbers, right? So we'd have 1 plus 8 plus 21, it's 30. We'd have 2 plus 10 plus 24, that's 36. We'd have 27 plus 12 plus 3, it's 42. And so that would be what row 1 would be replaced by. And so why can we add linear combinations of any row to any other row and still not change the determinant of the matrix? The reason why is because if you were to think of adding or subtracting, because I mean subtracting is just adding the negative, if you were to think of adding or subtracting linear combinations of a row, which is really a vector, to any other row, what you're doing, in essence, is just a rigid transformation of the parallelpiped that the vectors geometrically represent. For example, in R2, if you've got this vector here and this vector here, and then I don't know, this is the vector, well, that would look like about 3, 1, and this would look like about 2, 3. And so if you were to add, say, let's call this vector v sub 1 and v sub 2, whoop, and you were to add v sub 1 to v sub 2, what are you going to get? Then you would just call it v sub 2 prime for a different v sub 2, and that's going to be 5, 4, because you just add the corresponding entries together. And so all that has done, basically, you could kind of think of it like this. See, hopefully this will, dang, it grabs the whole thing. Let's see if I can, it basically is just moving around this vector right here up to, let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4 to here. And so it's just shifting or translating the parallelpiped, right? You're just say moving around on one axis by some amount and on another axis by a different amount. So in the case of this example, we added v sub 1 to v sub 2. So we just shifted the whole parallelogram, in this case, since it's an R2, we shifted it 2 units to the right and 3 units up. And of course, shifting and translating any shape does not change its volume in whatever space you're in. And so that's why you can, if you think about it geometrically, that's why you can do this Gaussian row operation and the determinant will remain unchanged. So now that we know we can do these row operations, how does that help us to show that linear independence implies diagonalizability? So let's start with our original matrix right here, right? This matrix. And we're going to interpret it as a coefficient matrix, right? So this is the general matrix, but to help make the proof kind of a little more readable, I guess, or for explanation's sake. Ooh, I don't want to take away the linear independence part. Okay, go like that. Copy. And then let's see if I could paste it. Wahoo! Okay, so if we've got that matrix right there, then we can interpret it as what's called a coefficient matrix. I'm just using this particular matrix as an example because I think it demonstrates my point a little clearer rather than kind of going totally general with you at once. But understand that by choosing this matrix, I'm not limiting myself or anything. I'm just kind of making it easier for you to understand. It's not like the proof is any less meritable. So we interpret this matrix as a coefficient matrix. And so what does that mean? It means basically that these are all scalars inside of this matrix. And so if it's a coefficient matrix, then it's being multiplied by another matrix with 3 variables, x, y, and z. And it's going to be equal to another matrix with new scalars, say, I already used C, k sub 1, k sub 2, k sub 3, where those are all just constants. And so what this whole thing is doing here is it's just a compact way to write a system of 3 linear equations in 3 unknowns. In other words, we would have, if we were to expand the first row of that coefficient matrix, we would get that a sub 1x plus a sub 2y plus a sub 3z is equal to k sub 1. If we were to expand the second row, we'd get b sub 1x plus b sub 2y plus b sub 3z is equal to k sub 2. And then finally, you can probably see it, c sub 1x plus c sub 2y plus c sub 3z is equal to k sub 3. And so this looks a lot uglier than this, in my opinion. And so this is how you would set things up if you were to do what's called Gaussian elimination. And now I'm just going to have to assume at this point that you've seen Gaussian elimination, because this video would be too long if I tried to explain that within this video as well. So that's how you would set it up if you're going to use Gaussian elimination. It just looks nicer and it's going to be easier to do. So now going back to the linear independence, we have to have linear independence in this matrix. So what that means, what that implies, is that this entire system right here, right, is going to have exactly one solution. Why? Because if we've got linear independence, then we could think of all of, I should have kept, let me just write the first one again. A sub 1x plus a sub 2y plus a sub 3z is equal to k sub 1. What this represents geometrically is a plane. It represents a plane in 3 space. And likewise, if we were to go along the second row, we'd get another plane and a third plane. And since they're all linearly independent of one another, that means that the 3 planes aren't scalar multiples of one another in their planar equations. And so that means that, say we have 2 planes, say these 2 planes, when we write them out like this, they're going to intersect because they're linearly independent and they don't coincide with each other, and they're going to form a line. And then we would have this third plane right here, and it's going to intersect somewhere on that line formed by the intersection of the first 2 planes. And that intersection between the line and the plane is going to create a point, and that point's going to be our solution. And so we'd have exactly one solution given linear independence. So now, since we know we have a solution, exactly one solution to this system, then we can use Gaussian elimination to solve that system. That's the whole point of Gaussian elimination. And the whole idea with Gaussian elimination is that you, let's call this whole matrix here, let's call it matrix A. The whole idea with this Gaussian elimination is you just multiply by A inverse on both sides. And since we can do that, we know that A is invertible in essence because the system has a solution. And so since the system has a solution, A has to be invertible in order to use Gaussian elimination. And we know we can use Gaussian elimination because we have a solution. So since we know we have an inverse, that means that now we would just, after we multiplied by A inverse on both sides, we'd get A inverse times A, which would just be the identity matrix I, times this whole thing, XYZ, and then we would have, I'll do A times the vector X, because this is really just a vector, an n by 1 matrix is a vector, and we'll call this K, right? This end matrix right here we would call K. And so now we know that has a solution, but if we were to go from A to multiplying by some matrix to get it to be the identity matrix, which in 3 dimensions is 1, 1, 1, 0, 0, 0, 0, 0, 0, then that means at some point we would have had to have a diagonalized matrix where instead we just multiplied by, like, say, in order to have an identity matrix, you'd have to have a diagonalized matrix because let's say these were instead K sub 1, K sub 2, K sub 3, which is what they would be. They would just be different constants. When you actually would do the Gaussian elimination, if you've ever done Gaussian elimination before, you know that that's what happens. They're just different constants. And then you end up multiplying that first row by 1 over K, the second row by 1 over, or you multiply the first by 1 over K sub 1, you'd multiply the second row by 1 over K sub 2, and the third row by 1 over K sub 3. And that would give you the identity matrix. So if you have an identity matrix, you have a diagonalizable matrix. And so that shows that linear independence implies diagonalizability. And now, to go from the normal matrix that we have right here to a diagonalized matrix, what that corresponds to geometrically, like I was saying before, is just rigid transformations. That's why we can use those Gaussian row operations. Now, the rigid transformations, they preserve the volume in n space in say Rn. That's all I'll denote it. So what that means now is now we have a matrix of the form K sub 1, K sub 2, K sub n. Right now I'm going back to n dimensions. Then we've got zeros everywhere else. Zeros, a bunch of zeros, all zeros, except along this main diagonal. 0, 0, 0, 0, 0, 0, a bunch of zeros, right? And so what this matrix now represents geometrically is a rectangular prism. Isn't that just so cool? Because now notice, in the x sub 1 direction, we just go out k sub 1 units. In the x sub 2 direction, we go out k sub 2 units. So on and so forth, right? In R3, if I have the vector 1, 2, or if I have the matrix 1, 2, 3 along that main diagonal, and then 0, 0, 0, 0, 0, 0, all that geometrically would represent is in 3 space, we would go 1 unit out in the x direction, 2 units out in the y direction, and 3 units up in the z direction. And we would just get a, hopefully you can understand my drawing here. We just get a rectangular prism. And so if this rectangular prism, now obviously, its volume is just the product of all the lengths of its sides, and the lengths of its sides are given by these numbers here. That's why another way to think about, that's why you can just multiply along the diagonal to get the determinant of a diagonalized matrix, because the determinant then is just the volume of this rectangular prism, right? The determinant is found by, in a diagonalizable matrix, just by multiplying across this diagonal. And that obviously is the same thing as just doing length times width times height in this example. And since we went from a parallelpiped to a rectangular prism using only rigid transformations that preserve volume, then that means that the determinant of our original matrix is equal, I'll say the determinant of the original matrix is equal to the volume of the rectangular prism. And since the volume of the prism is the same thing as the volume of the parallelpiped, because we use only rigid transformations to get from one to the other, then by transitivity, the determinant of the original matrix is always equal to the volume of the parallelpiped. Isn't that so cool? I just think that's such a powerful fact about determinants. And so this proof right here, we can now say in big red, Q, E, D. And we're done.